This episode is brought to you by Cisco Educational Premium.
Riemann decided to take it one step further. Instead of selecting just one world to play in, why not combine them all into one? During his inaugural speech in 1854, he laid out the grounding work for the geometry where the curvature could differ from one place to another. One path might be flat, another path might be slightly curved, and another path might have very strong curvature. This geometry could extend to infinite dimensions. Another breakthrough came in 1868 when Eugene Peltrame proved that hyperbolic and spherical geometries were just as consistent as Euclid's flat geometry. In 1905, Albert Einstein proposes the special theory of relativity, which is based on just two postulates. One, the laws of physics are the same in all inertial frames of reference. Two, the speed of light in a vacuum is the same for all inertial observers. What he is saying, in other words, is that space-time must be relative. But according to the legendary Isaac Newton, the force of gravity is inversely proportional to the distance between two objects squared. And so, this distance, according to Einstein, is no longer well defined. So, what gives? In whose reference frame are we measuring? So, Einstein had to find a way to reconcile relativity and gravity. 2 years later, in 1907, Einstein had the happiest thought of his life. He imagined a man falling off the roof of a house. He realized that while the man is falling, he would be absolutely weightless, and if he would just let go of an object, it would remain in a uniform motion relative to him. It would be just similar to being in space, not near any masses, floating around in a spaceship at a constant velocity. And that is an inertial observer. The great Einstein realized that they are not just similar, but they are identical, because there is no experiment you can do to determine whether you are in free fall in a uniform gravitational field or whether you are in deep space, not near any massive objects. In other words, you can produce a required artificial gravity by appropriately accelerating an object. But wait a minute, if gravity is not a force, how do we then explain things like the space station orbiting Earth? Should it fly off in a straight line if of course no force is holding it? Well, astronauts in space station also feel weightless, and they feel just as though they were traveling at constant velocity in a straight line. It feels like that because that's precisely what they are doing. They are traveling in a straight line. Wait, what? How does this straight line then appear curved to a distant observer? The thing is, the spacetime that straight line is on is curved. Massive objects curve spacetime, and objects moving through the curved spacetime follow the shortest paths through the curved geometry. We call these paths geodesics. So while astronauts in the International Space Station are following a straight line, it appears curved to a distant observer because the Earth curves the spacetime around it. In 2014, astronomers briefly observed a supernova, a violent and extremely bright death of a star. In fact, they saw the exact same supernova in 4 different places. How? While in between the supernova and Earth there was a massive galaxy which curved spacetime. So light from the supernova, which was spreading in different directions, has so many paths to reach the Earth, and 4 of those reached the Earth at approximately the same time. The galaxy had functioned as a massive gravitational lens. On the 11th of December 2015, the other light arrived, and the same supernova was seen once more.
Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.